somebody's just in the waiting room. All right. Okay, over to you, Mike. You can proceed with your session.
Perfect. I'll just let Shannon get signed in here and then I'll get going. Okay, I think he's in now. All right, good morning, everybody. We've made it to week 11. So thanks for getting up and sharing your early mornings with me. It's really early for me. Unfortunately, I'm still getting my coffee into my system, getting woken up. So with this being the last session, we're going to do the water sampling and analysis today. Now conclude the bulk of the content for getting you guys prepared to write the exam. Next week, what we'll do is I have chosen 50 questions for you guys. And what I'm going to do is I'll put a question up on the slide and then you guys can answer me via the chat function, A, B, C, or D. And if there seems to be an issue with the question or there's a problem, we can have a quick discussion about it. So what I would suggest for you guys is go through the tutorials again, all the ones that we've gone through and any reading material that's been supplied and allows us to have that discussion at that point. I've picked those 50 questions up just to make sure to see where your comfort level are. Some of them are kind of tough and you'll have to really think about it, but it'll show me how much you guys have paid attention and learned from the content that's been put forward. For this one here, again, water sampling, really important for not just you guys at the treatment plant areas, but also people who are in the distribution as well. You know, we know throughout the processes that we have to test that water to make sure that the processes throughout, whether that's raw water coming in and going all the way through the process to water leaving, has to have a certain quality, and not just for people's health, but to make sure the processes within your treatment plant are working correctly. But once it leaves your plant, it has to go in that distribution. So it goes through pipes, it goes through those reservoirs we talked about. And we got to make sure that throughout that transmission, that that water is also tested to make sure it still maintains the quality that it had when it left the water treatment plant. And sometimes we have customer complaints and we have to go to people's homes and see, you know, what happened. And a lot of time it's what's happening inside that person's home or a business that causes adverse effect in water quality. We find that all the time. Right now for here, especially in Canada, as it warms up, people start using more water and our flows will double. So you can imagine if you're flowing very little water and then all of a sudden lots of people turn their taps on, it's almost like a flushing program, right? It's almost like people turn on their tap and away they go. And we do get a lot of complaints because with more water going through the pipes, the more scouring it happens and we get yellow water complaints a lot. I will go from my normal 7 or 8 million liters a day to almost 40 million liters a day in a matter of about a month's time here. So you can see that we really have to change how we do business here. So let me get the slide deck up here. Share my screen. Here. Can you guys all see that? Give me a thumbs up if you can. I'm just going to move my chat guys over here. Thank you. Perfect. I have way too many screens here. I got to put chat guys over here and presentation. So this is week 11, water sampling, monitoring, and analysis. And again, what we're going to be doing here here. This is an overview of the lab stuff, and not every place does this kind of testing. Some places do very minimal testing by the operations staff, and some places have specialized laboratory staff that will come in and do a lot of these tests. Some of the tests we'll talk about, we send away to get processed by an accredited lab. What I find here for us, we will do here, if I plant this side, we of course will do our chlorine residual, we'll do our basic chemistry lab, which is your conductivity, alkalinity, hardness. We're testing for pH, anything that can change day to day. But anything big like bacteriological samples get sent to an accredited lab, which means it's specialized to do that test. And we also 3 times a year, we send out a scan, and it tests for everything, all the metals and pesticides and anything that's in the water. And it gives us a good idea what's happening in our sources. So we will test all our raw water sources as well as our blended sources here at the plant. So, and that's a really good idea to do once in a while to make sure that there is no changes in your source water, because what happens if there is, then you guys have to follow suit in your treatment process. So what we're going to really concentrate on today is the stuff that you guys as operators will be doing. We're also going to name some of the tests for testing for pH and temperature, dissolved oxygen, and why we test for this stuff. Hardness and chlorine, turbidity and alkalinity. These are all really important things. We learned that as we went through the lectures, and some of these things really do affect how our other treatment processes go. We're going to list some of the equipment that are used and doing some of these tests. Importance of calibration, right? Nothing is you know, you can't take a meter out of the box and it's going to work. Sometimes they have to be maintained and calibrated to make sure that they're going to work properly. Sometimes when you collect samples, you got to preserve them or make sure that, you know, especially here, our biggest thing is I'll send a crew out to do sampling, and you can imagine if the temperatures are in the minus temperatures, I got to make sure that these don't freeze, right? And in the summer, we can get some pretty hot temperatures in the summer. Granted, probably not as hot as what you guys experience, but for us, it's pretty hot, and we got to make sure that those samples don't get into a temperature that will make them degrade. So let's start this. So again, the most important part of any of our water sources, whether that's creek or stream or river or lake, it's not the stuff that we can see, right? All the stuff we talked about in our treatment is making things visible so we can remove them. But when you take a glass of clear raw water, it's really hard to tell you, hey, that's got this much pH or this has this much iron in it, because we don't know with the human eye. We have to rely on instruments and to tell us what exactly is going on in there, whether that's iron, manganese, pH, alkalinity. Nobody can see that without doing these simple tests. So we have to be good in this lab to detect these issues, whether that's chemical or physical or microbiological, so that we can treat that and make sure that it's going to be safe for our customers, or it's going to be, we have the right treatment techniques to be able to treat this water. So the most important thing is stuff we can't see. So again, we just don't do this to satisfy the curiosity. We want to make sure that things our treatment process is good. And maybe if there's something upstream, right? For us here, we have a lot of logging, right? Paper production that happens in our watershed. Some areas in Canada also have mining. So there's activities that happen that could degrade the water or change how the water happens. We also, unfortunately, get a lot of fire activity. With so much wood area here, we get the forest fires, and that does change how water goes through the environment into our receiving body of water. So we're going to look at our water quality parameters and some of the techniques and how to treat this water or get it tested. All treated water should be tested for a number of reasons, and we kind of talked about that. We want to make sure that we're always, number one, our customers getting good potable water and that it's safe to drink. And not just that it's safe to drink, but it looks safe to drink. And because one of the things I always was taught is that if the water doesn't look good, your customer is going to look somewhere else, and they might choose a source that might not be as good. I have an example here. Back in the 80s, we didn't have a water treatment plant here, and the water was really yellow. And so what people were doing is there was some natural spring water coming off the side of a hill, and people would take their cans and their bottles and they would fill water from the side of the hill. What those people didn't know is that, yes, that was nice, clean, clear looking groundwater, but it was actually flowing underground, and it was flowing through a garbage landfill as well as a cemetery. So that water was moving through those two things before coming out the side of a mountain. It looked clear, but it was not safe to drink. And a lot of people got sick because they felt that clean, clear water, by visually looking at it, was safer than yellow water or water with some that was safer to drink. So always be careful. Make sure that the water not only is safe, but it looks safe, so your customer has that confidence. You also want to determine how effective your treatment is, right? So that's a big thing. You're going to be testing water throughout your process to make sure that it's removing what it's supposed to remove at that step in your treatment process. And if it isn't, then you're going to try to pick a process or adjust your process or your chemicals to make sure you're getting that desired result. Again, no matter if it's groundwater or surface water, we know that there's a big difference between the two. We need to test it in accordance to the regulations that are set out. I'm going to have a little different regulations than what you guys will have, but you got to make sure that you know those regulations and that you're testing for what you need to test for. It's super important that you're providing that safe, potable water. The biggest part about that is the microbiological component, right? You don't want any coliforms or any bacteria in that water, because that's what's going to cause people to get sick. And that's definitely what we don't want. And again, they're harmful, right? Coliforms are the big one. We'll talk a bit more about coliform bacteria, but they are the big one. They themselves aren't necessarily bad, but they represent that if I see a coliform in my sample, it's an indicator that, hey, there's probably more issues there. There's two types, and we'll talk a little bit about those in a little bit: total coliforms, and there's also like a fecal coliform. And the fecal coliform by far is the more damaging of the two. Again, good quality drinking water should not contain any of these coliforms bacteria. So when I do a sample, usually it's a 100 ml sample, and I'll fill that up. It has a chlorine deactivator in it, and we'll put the water in there. And sometimes in some methods, they'll put the bug food or the media inside the vial. And other times what they'll do is they'll pour that sample into something called an agar plate. And that's this picture here. That pink liquid is kind of food, right? And it will cause any coliform bacteria to form or to come about. And you can see here in this particular example, a lab tech will incubate this particular sample. When he brings it out and he sees these big pink dots here, that's going to tell you that there's coliform bacteria, and that's not a good thing. But you'll also see that there's other colors in there. There's a kind of a dark green one and some brown looking ones in here, and those are also bacteria. They might not be harmful ones, but they definitely are. And this is what they call an HPC, or heterotrophic plate count. I actually count those as well, because that tells me if I see some bacteria starting to grow in my pipe network, it tells me it's time to flush. So the more and more of these black little dots I see up here, I make sure that my system gets flushed at that point. They're not harmful, but it is an indicator that things are starting to build up, or the water potentially could be getting stagnant and I need to turn that water over. So I kind of keep a really good eye on these, all the colors in this, what they call this agar plate. Surface water, again, it's going to be the one that's most involved with the environment. It needs to be monitored for all these items. Total organic carbons, phosphorus, color, turbidity, and these are all things that, because the water is open to atmosphere or open to human interaction, there's a big chance that this water can be polluted or get polluted as it goes through the environment. Again, one of the biggest things, and I can't stress that enough, is watershed management. And that's making sure that where our water comes from is really secure, right? And that's whether it's industry or human interaction, but you're trying to keep it as clean as possible, because the better you can keep that source, the easier your treatment or the more consistent your treatment can be. I know a lot of watersheds that they allow recreation, 4x4 vehicles go in there, motorcycles, and they add a lot of mud and they garbage and they make a mess, right? And that's what you have to make sure, that your source of supply is secure. When you're looking at potential sources, it's not only important to consider the quantity of the water, but also the quality. And also thinking about too, now the big thought process on top of this is making sure you have more than one source potentially. We're really lucky here that I have a creek and I have a lake, and I can take the two and blend them together, right? So if there was ever a problem with the lake and contamination, then I can go to the creek and vice versa. A lot of places don't have that luxury. They have a lake or a single source of water. And if that water source gets polluted, they have no other source. And that's scary to think about. So making sure that you plan ahead. What would you do if your contamination was widespread in your source water? Can you treat that contamination? Or if you can't, what's your options? Again, throughout the system, lots of contamination. And so you have to make sure that you're built either a secondary source or the treatment process is going to be as such that would treat these issues. You look at these things called multi-barrier treatment systems so that we always are making safe potable water. So let's talk about water itself, right? In its purest form, it's 1 oxygen, 2 hydrogen, H2O. That's what it is. It has no color, taste, or odor. It is like nothing. Think about pure water. And that's like, say, a creek water. It's very aggressive. It's our snowmelt for us. Very aggressive. There's no color, there's no taste, there's no odor. And as it passes through the hydrological cycle, whether that's groundwater or comes through, it's going to start taking on colors and minerals, right? As it sits in the ground, it takes on definitely the calcium and magnesium and other minerals to make it harder. If it's surface water, sometimes it takes on colors from leaves and dirt, but really it very different depending on what the substrate it goes through. Water, when it say rainwater, is going to be very aggressive water that has nothing in it. It's a universal solvent and it contains nothing. As it goes through the atmosphere, it's going to start taking stuff in like a sponge. And that's why everybody's water will taste a little bit different. My water is going to taste different than your water. And if I go to a neighboring town, their water is going to taste different as well. And it's only because where did that water flow through, and what path did it take? So if it's underground for a while through this type of stone or this type of rock or this type of substrate, it's going to take on that particular characteristic. Keep in mind, like what you guys are used to for taste is minerals. So calcium and magnesium. In the bottled water industry, what they do is they take water and they strip it right back down to this H2O, right, purest form. And they use like reverse osmosis or something. And that would taste horrible and it's not good for you. And we learned that a couple of lessons ago, that water that has no minerals in it is not a good idea. So reverse osmosis water, not a great idea to drink. So what bottled water companies do is they actually have minerals that they add back into the water. And it gives it that taste that you're used to from bottled water. And if you read the bottle, they'll say remineralized. And so they'll do stuff like that to give that taste, that perfect taste every time. Three main categories of water quality, and we're going to talk about all three. One's going to be a physical, chemical, and biological. And those are the three big ones. And these are the things mostly you guys will be testing in your little labs. One thing about physical, and we look at these things, and we'll talk all about these: turbidity, alkalinity, color, temperature, hardness, taste and odors, and total dissolved solids. One thing about this, these are all very hard to control, right? Like stuffing like temperature, very hard to control. This is really the water when it comes from the environment. This is what it is. Also, another thing about this is that none of these things here are going to harm you. Yes, turbidity, we don't like it, but it's not going to make you sick, right? These might make treatment processes tougher, or we'd have to adjust these things to make our treatment process easier, but none of these things are going to harm you. And they're all physical in appearance, and it makes our customers happy and builds confidence. But none of this stuff is really going to make you sick. So let's talk about turbidity first. Turbidity, again, is the cloudiness. And they always trip you up on the test because they'll say, hey, what's the dirty, or the, if you got solids in the water, is that turbidity? That's suspended solids. So make sure that the dirt in the water is suspended solids, where the colloids and those really small particles are going to be turbidity. And you can see here, it's the cloudiness. You can see on the far left of the photo, it's nice clear water. It's not very cloudy. And now you got that yellow haze to it, a more yellow haze and almost like a brown type haze. And think about that haziness or that cloudiness, and that's going to be your turbidity. Turbidity are measured in something called an NTU, and that's actually pronounced nephelometric turbidity units. And basically what they are is these are quantified using an instrument called a turbidimeter. And this turbidimeter passes a beam of light, and we're going to see that in a second, through a water sample at 90 degrees. And that's the important part about if you get a test question about measurement of turbidity, it's always done at 90 degrees. And we'll talk about that in a second. There's a number of different styles, and I got some pictures here of some different turbidimeters. First one you're going to see is a lab style turbidimeter. There we go. This one's a lab style. You can get them a little smaller than this. This is one from one of my old labs. For operators in a lab, they're going to be testing turbidimeter or turbidity with this type of meter here. And we'll talk a little bit about how these turbidimeters work, so you guys have a better understanding of how it works. Also, there's wall style, like this is a continual measurement. I have two different styles here. This is actually in my plant, the one on the, where's my little pen here? Oh, this guy here, this is for my lake water coming in. It's measuring that. And this is an older style turbidity meter here online, and it's coming from the creek today. You can see 0.58 coming in and 0.57 coming in this particular photo. These are online. And again, they all work kind of the same. And we'll talk about how it is. Basically, the instrument compares the amount of light that is scattered and absorbed by the suspended material, right? That cloudiness. The more light that is scattered, the higher the turbidity. So let's take a look at how that looks here. All right. You can see in my drawing here. So what they do is you shine a light beam. So we start over here. We got a light beam, and it's going to shine a light through the lens. And it's going to shine it into the sample. What's super important here is that it's got to shine it through the sample, but all the glass as well, right? It's got to go through the glass, through the sample, out through the glass. If the light meets the end, that's one thing, and the scattered light at 90 degrees gets read by a detector. So you can imagine here, the problem people don't understand. Let me make a little drawing here if I look at it. Here's my vial with turbidity, and you got product on the inside. As the light goes in here, it's got to go through the glass, through the sample, out through the glass. If there's any imperfections in that glass, or scratches, or you didn't clean it, or a fingerprint, that's going to change how much water or how much light can get through and how much light is scattered. So I can't stress enough how you have to take care of your water vials and make sure they're not scratched. That's the first thing I do when I go to a plant. I'll check and see how clean those vials are and make sure if they're scratched, they should be replaced. They got to be super clean too. And I never ever touch in the area where the light's going to shine through. I might grab it at the top or at the very bottom, but I try to keep my fingers off anything in between. But keep in mind, always 90 degrees. You can see how really easy that the vial can make your sample go right sideways. So make sure those vials are super clean. And we saw that earlier. Like I said before, though, turbidity poses no negative health effects. It provides, though, unfortunately, all those little specks, bacteria can grow on a piece of turbidity. So that's the biggest one. If there's more turbidity, it's harder for the chlorine to deactivate bacteria. So that is why they think, if there's more turbidity, there's usually more contamination or more potential for bacteria to grow. So you have to up your chlorine a little bit to target that. So always remember that. Always bring your chlorine up a little bit if your turbidity comes up. For here in Canada, the maximum allowable, or MAC is what they're going to call it, for water entering a distribution system is 1 NTU. From the naked eye, you wouldn't be able to tell, but that's, it looks pretty clean to me. So 1 NTU is usually the standard for water entering the distribution system. I think ours today is, I think we're at 0.04 would be our NTU going into the distribution system here today. And I just checked it before our lesson today. So we're doing okay, but sometimes in the system itself, right? Things move around, water moves at different rates, carries different things in it. So we always have some buffer room. In this case here, the 1 NTU rule. Let's talk a little bit about alkalinity now. And we talk about, to me, alkalinity is super important. It's by definition, it's the water's ability to neutralize an acid or resist a pH change. It makes the water stable. The more calcium carbonate, the more protection your water has, because you want that steady state or that steady pH. Alkalinity also, we know, is really important in the coagulation process, right? We know that it uses alkalinity in the water. So as we put more coagulant in the water, it takes alkalinity out. And we know here that if we take alkalinity out, it makes the water less stable. So it's a balance. We want to kind of keep stability in that water, because that stability, that calcium carbonate or CaCO3, will keep the pipes safe. If you don't have a lot there, metal pipes, this is ductile iron, cast iron, copper, all these pipes are at risk for causing breaches and holes, and that's something you have to really look at. Also can cause a lot of red water complaints, right? So and also you don't want that. The other thing is alkalinity is always and usually expressed as the equivalent concentration in milligrams per liter as calcium carbonate. So again, calcium carbonate is really important. And that's basically, that's that water's protection or the stability of the water. I like a water with a little bit of calcium carbonate. I did a trial here last week. I changed a coagulant that uses less alkalinity, which gave me more alkalinity in my water leaving. It made my water more stable. One thing they do is they use a measurement tool called an LSI, and I think we touch on it later. And that stands for Langier in Saturation Index. And that's a measure of how aggressive or corrosive a water is, or is it scale forming? And I always like a little bit of calcium carbonate, and I like a little bit of scale forming, so that we're not running into issues with pipes being damaged due to aggression. Let's talk about color now. So color is, again, can come from a number of different sources. It could be natural, right? And that we've seen that with the iron and manganese, that red and that black color. It starts making our water look like a little bit like tea. We also have vegetable origins, right? And when I look at vegetables, you're looking at leaves, right? And that is tea. When I put a tea bag into hot water, what happens? The leaves impart that color, that tea color into the water. You get the flavors and the colors in the water. And that comes from humus material or something called a tannin. And that's exactly what we see there. In nature, we're seeing the same thing. The water might not be hot and it might not be as quick, but we do see definitely leaves and vegetation as it decays or changes form, it will impart a color into the water. There could be some discharges from mining or processing industry. It can put different waters in here, different colors, and that's something you have to always be aware of. Is there anything in your watershed that could cause any of this issues here? Could be wastewater from a town downstream, but you have to always be aware of where does your water come from? Is there any industry in that area that's going to cause issues? Here's an example of color, right? No treatment and treated. Definitely you do not want to drink the water on the left. That looks awful. Color comes in two forms, and it's measured. Both these forms are measured. One's called a true color unit, and one's called an apparent color unit. You can have simple measurements are made using a color wheel. And these old color wheels used to be, and they're used all the time. I actually have 2 or 3 of them in the office here. They used to put a vial in and spin the top to make that work. Let me go grab mine for a second here. And these were used quite a bit. I don't think these have been used. So this would be typical. Inside here, there's a color wheel, and I can spin the color wheel. What I'm going to end up doing is I'll put a vial of water that's probably distilled, and that's my blank, and then I'll put another sample in that would be my sample, and I'd hold it up to the light and look at these two windows, and I'd spin the color wheel to the right color. And again, the problem with any of these is it's very subjective, because what I see as a color, you might see something different. So very, very subjective testing. But it crude, but it works. And these are color wheels. And these were used for color and chlorine, actually, a fair bit. Early chlorine kits used a color wheel. Again, quite old hack units. Nowadays, though, now we have more sophisticated units that we measure color with, right? We'll have these big spectrophotometers and whatnot that will give us an actual reading, right? An actual number. It takes the how subjective that is out of the equation. There's two types, like I said, apparent color and true color. And the big difference is apparent color is a direct measurement of the sample. So I'm going to go in, I'm going to take a sample of my water, and I'm going to measure it directly. And it's going to be looking at two things, the color that's embedded in the water, the dissolved, and the color that's floating in the water, the non-dissolved or the suspended. And it should always be higher than the true color. If I take that apparent sample now and I'm going to filter it through a set of filters and capture all the suspended and just measure the dissolved, that is a true color. And true color is the filtered measurement of the sample. It's the color that's embedded and it can't be removed, you know. So always think about that. Apparent color is always suspended and dissolved, whereas true color is just the dissolved. The suspended has been filtered out. And those are the two types of samples. In and around there, and again, really hard for the naked eye to see, is the maximum allowable concentration, or the MAC again, is basically an aesthetic objective. And that's just saying, that's what we're trying to go for. It's really hard to do sometimes, but 15 true color units, which is really, really hard to see with the naked eye. It's measured to a standard called a platinum cobalt standard, and that's what they'll call it. So when you look, it's always platinum cobalt standard. And again, colors removed through the coagulation process. So that's super important also to think about. I've got one more unit to show you here, since we're on this topic. You know, we've come a long way, I think, in the industry. And I'll show you this. This is a Turbidity Meter that was used like not too far long ago. And look how old this thing is. And we got much more sophisticated units now, but this is an old NTU meter back in the, you know, probably early 80s. They were still using this type of stuff. A lot older. Again, our turbidity meters are much more robust now. Let's talk a little bit about temperature. Temperature is probably one of the harder characteristics or parameters to control. But it plays a major factor in how we add chemicals and you know, and again, how our bugs grow out there, especially if you got a surface water source, right? a lot more bacteria happens. The other thing we don't talk about a whole lot is the algae growth, right? And when the conditions are correct, that's algae, and these bacteria can grow a whole bunch, and that plays havoc with your chemistry. Also on the cold side, and we'll talk a little about that too, what happens when it gets cold, and we'll have to kind of look at what do we need to do to make sure that we're adding the right amount of chemicals. So temperature makes a huge difference, but it's also really huge to control. Like, it's hard. Our water here right now is probably going out the door at 4 degrees C. In the summertime, it could be 18 degrees C. That's a huge difference in water temperature to try to treat. And again, fortunately, the water when it's 4 degrees right now, it moves through the system so slow and it's quite stable. Whereas the warmer water at 18 degrees is moving through so fast. But again, because it's warm coming in, it's warm into people's taps. And that's, I mean, I've had a lot of complaints, and you guys in the systems will laugh, but I've asked, they go, well, can you make the water colder? I wish I could, but unfortunately you can't make it colder or warmer. It's just, we get water at a certain temperature, and we do our best to provide, that water to our customer, but it's hard to change temperature. One thing about higher, especially when it comes to do with the test, is that higher temperature water can increase the rate of chemical reactions. It happens quicker. It's think of chlorine in coagulation. It happens very quickly. Reactions love hot water. And we look at that, we talk about tea, right? Tea, when you put tea bags into cold water, it doesn't quite work as well as if you put tea bags into hot water. And then it works really well. The reaction happens. Same thing with any sort of chemical reaction, whether that's coagulant or using any sort of chlorine type product. The problem with higher temperatures, though, is that there's usually more bacteria as well. So you need more to combat that part. Lower temperatures. Water tends to have less bacteriological because everything's, cold. But the reaction takes longer. So you need more chlorine or chemical because the reaction. Think of it this way. Nobody likes to work when it's cold, especially here. If I have to send my guys out and it's -20, -30, nobody really wants to work when it's cold. So always think about that when you're dealing with your chemistry. Nobody likes to work when it's cold. All right, let's talk a little bit about hardness. And we talk in great depths in our lecture about water hardness and what that really means. And again, it really comes down to the amount of dissolved minerals. And the minerals of choice here are going to be calcium and magnesium. Those are the main ones, okay? They also make up that calcium carbonate that we talked about, right? That makes that water more stable. This gives the water also the taste. This is the number one thing. This is what gives that water the taste. And again, depending on where your water comes from, whether it's a well or surface water, it's going to be different type of hardness. How do you know? Again, if you ever showered in a place where it has different water and you're soaping yourself up, you know that soap will work differently. Soft water makes a lot of soap, whereas hard water makes very little soap. You'd have to put a lot of soap on your hands and really work it, and it really doesn't have a lot of suds, right? And when you rinse off, it feels slimy still on your skin. You're like, ah. Whereas, say, a harder water is much different. Your skin feels much drier, Yes, the slide before did say lower temperature, the more chlorine is needed. Only because reactions go much slower when it's cold. So it's funny that that when the water's hot, there's more bacteria, and that's why you need more chlorine. When it's cold, there's less bacteria, but it takes longer for that reaction to happen. So sometimes you also have to have more chemical, chlorine included. It's more stable and it lasts longer, but you also have to compensate for the slow reaction time. So also hardness here can also lead to scaling. And this is a really extreme sample of what could happen. This is an old drainage pipe, and over time, you can see how the scale has built up. Now, I'm not sure how a piece of tree got stuck in there, so I'm pretty sure this isn't a water pipe, but this is just an example of what an inside of a pipe could look like over time if it continued to scale up like that. Quite significant, if you ask me. Again, when we talk about that acid forming or scale forming, I always want a little bit of scale forming. Unfortunately here, this is a really heavy duty scale forming. That's also not good as well. Okay, just before we go for a quick break, taste and odor. And again, that's another one that's really hard to judge, because what you can taste and smell as a customer is everybody's going to be a lot different. I find people who are new to the area or have just moved to town are usually the best judge of taste and odor. But you got to be careful. What is the taste and odor? Is it different tasting than the water you're used to, or is there truly an issue? And I find, even if I go to another community, I don't like the taste of their water, or because it tastes different. I'm like, oh, this tastes weird. And it's not necessarily because it's bad. It's because you're used to the taste of your water, and you get really used to that. And again, it's personal preference and sensitivity. There's no objective measuring method for taste and odor. They'll use something called a threshold odor number, or a TON, and that is the mechanism that is used. And again, it's super subjective, because what I'm going to think of a taste and odor is going to be different than my partner, or different than other people I work with. It's always different. Unfortunately, taste and odor is going to be our #1 customer complaint, right? Oh, it tastes like this. But there's certain things you got to remember when we talked about, taste and odor. Really pay attention to what the taste and odor could be. It's a grassy, fishy smell. It could mean maybe too many organics in there, or a stagnant line. If it's chlorine smelling like a swimming pool, it could be lack of chlorine or not enough oxidation by our disinfection process. Maybe it tastes like a medicine-y taste, and it could be from algae, right? So these are the things that are really important to understand. What is the taste and odor? What, does it smell metallic? What's the issue? And that's really important to figure out what it could be. Number of different sources too for taste and odors, right? Again, inorganic salts, and that's going to be some of your minerals, metals that are in there, organic chemicals that could do it. Products of biological growth, maybe iron bacteria, that happens. But one thing's for sure, when you add chlorine to water with some of these things, the tastes always get worse. It creates a phenol taste, right? Or some sort of medicine taste for some of these products, right? Adding chlorine to water, great thing that they've done for disinfection, but it also can really cause a lot of taste and odor issues. And so we always have to be aware of that. All right, before we go to dissolved solids, let's take a 5-minute break. Ignatius, 5-minute break.
Sure, 5-minute break, okay. All right, I'll pause.
The second part of it, I just went during the break here and got some different instruments and stuff, so I'll be trying my best to show you on this camera some of the stuff as we go along here. All right. I can hear you, Ignatius. Thank you. Okay, so let's walk into dissolved solids now. And that's another big one that we talk about quite a bit. There we go. And again, that's a tough one. TDS, right? Or dissolved solids. And again, this is all these inorganics that are in the water. Again, really think about the minerals, right? All the minerals broken down. It's not just the calcium, magnesium, but this is all the ions with metals and whatnot, and they lump it all together into dissolved solids. It's definitely related to hardness and alkalinity, and definitely related to calcium carbonate. But it takes everything that's in the water. So anything that's dissolved from an inorganic perspective, they call it a dissolved solid, or a total dissolved solid is what they'll do. It's measured through something called a TDS tester, which is like on the screen here. And when you look at, say, a bottle of water, instead of saying how many minerals there is, they'll say what the dissolved solids are going to be. By definition, again, it's a collective measurement of everything, right? Of all the inorganics in the water sample. The problem is with high TDS, again, it's related, just like that pipe we saw. It's hardness, right? It will create excessive hardness. It could create some taste. Definitely not necessarily corrosion, but more on the scale forming side. If there's a change in your TDS in your water, that could indicate that there's some sort of contamination. You shouldn't have a big change in TDS. If you have a change in TDS, that usually indicates either contamination from another source. And that's super important. Not necessarily in your treated water, but on your source water, and making sure that the TDS has not changed coming in. Here's a really good chart here. Basically, you can see 0 TDS in the blue here is ideal drinking water, and that's reverse osmosis and microfiltration. It's not ideal because it has no minerals and it's not great for you. So always keep that in mind. 50 parts per million of TDS is usually like mountain springs or aquifers are a really, really pure water source. And that's now we're starting to get in a good water source area. As the water gets harder at around 100, right? You can see hard water TDS of 170. That's average tap water. That's where we're sitting in that purple range there. As we start getting into the yellow, it's high TDS, and that could be what they call mineral water or water from deep underground that has been in the ground for a long time, has a lot more TDS. As we get into the orange and red here, these are huge numbers, right? 400, 500 TDS. Those are really, really heavily laden with minerals. And it's probably not the best for you either. So we want to be around that. I mean, honestly, if I can be in the 100 to 200 range, I'm doing pretty good. That's usually where I like to be with it. I mean, in this example here, he's got 35. So I'd say that's pretty pure water. And the lower the number, the less minerals that are actually in there. And so you always have to be aware of that kind of. But TDS, it's really your flavor. So when you get your bottled water in the store and it says it's got 50 TDS in there, that is your flavor. It's added back in because reverse osmosis water is 0. So if it has TDS in there, it has not been reverse osmosis or it's been added back in. So be really aware of what you buy. I always like reading the label in your bottled water. And you shouldn't drink bottled water anyway. You should actually take it from the tap because it's just fine. So I always tell people that. On the flip side of TDS is basically electrical conductivity. And again, it's It's very, very similar. They can be used to calculate each other. Pure water, again, reverse osmosis water, does not conduct electricity. It has no ions in it, and the ions are needed to conduct that electricity. Water containing the TDS, or dissolved solids, and minerals do. Therefore, by measuring electrical conductivity of a water, you can make a correlation towards that total dissolved solids. They're inverse of each other. Here's an example here. You can see if I had a power source here and I put those two electrodes into this pure water on the left here, the light bulb does not turn on. It will not conduct electricity. You can see once I have ions, and this particular example has sodium chloride, so the ions of Na plus and Cl minus are in the water. Hey, that will conduct electricity, right? It will actually conduct it through that solution and again, light up the light bulb and complete the circuit. So that happens. Pure water, no ions, no TDS, does not conduct electricity. But also, a test question could be, TDS is related to electrical conductivity, right? So always, this is measured in something called a microsiemens, and that is the measurement for electrical conductivity, whereas the parts per million is used for the TDS. Those are the physical ones. Again, none of those things are going to hurt you. None of those things are going to harm you. They don't cause you any grief. They do change how we have to add chemicals, the amount of chemicals we do have to add, and the treatment process that we need to choose, right? So if it's hardness, or we have to get rid of minerals, or if it's color, these are the things we have to choose. And these are the processes that we have to use to remove those. And those are all physical characteristics and physical analysis of your drinking water. Now let's switch gears now. Let's go now to chemical. So chemical now, you're going to look at the big one. And I mean, I always use pH. That's going to be the big one. pH is going to be the first one we're going to talk about. A little bit about dissolved oxygen. And some inorganic compounds, And these are more the chemical analysis that we're going to make as we go through. And then the last one we're going to talk about is the microbiological component of it. But let's talk now about chemical analysis. pH. pH is always a really important one, right? It's again, that's that measure that describes the acidity or alkalinity or basicity of a solution. It's measured from a 0 to 14 scale. 7 is neutral. And again, here's my chart right there. And you can see all the different things we consume, right? You can see how we do. Milk is right in the normal, but lemon juice and vinegar, and I can put any sort of cola beverage, is going to be sitting around where the lemon juice is here. It's going to be in the 2 range. So significant acid and basic as we go. Again, for me, if I had my hand open and I had a little bit of battery acid on one hand and a little bit of ammonia or lye on the other hand, I would definitely want the acid, because your acids in your skin protect you, whereas the ammonia or lye will actually eat through the protection on your skin and cause some very serious burns. I've had burns from caustic before. It's not a pleasant thing. So always be very careful when you're dealing with products on either end of this pH scale. Some big things here to think about and make little notes about is pH below 7 and above 10.5 may lead to corrosion or incrustation of your water system. Again, this is that scale forming versus corrosive of your pipe. So you always, for me personally, I like a little bit of scale forming. That makes a whole lot more sense. But be careful with this. you want that as neutral as you can, but you don't want it to be very aggressive or corrosive. Another thing about pH too is to think about is the processes that you use. When pHs become low, okay, anything say under around 7 or below, it can actually do some real damage, soldering in your pipe networks and stuff. So this is the house, inside the house or inside a building. Some of the old solder was made of lead, and some of the materials that's used to put the pipes together can actually leach that lead and copper back into the water when it's below 7 pH. So it's always better to have, and I know the regulations for here in Canada has changed a fair bit now that pHs have to be much higher to limit the amount of leaching of lead and copper into the water. So keep that in mind. But unfortunately, the effectiveness of chlorine, when those pHs start to come up, it doesn't work as well anymore. And there's something called a ORP, or oxidation reduction potential. And what ends up happening there is that chlorine effectiveness, or how much acid and ion, we talked a little bit about that with disinfection, will change depending on pH. So as the pH starts going above 7, the effectiveness or the acid component of the dissociation of chlorine and water will actually cause more ions than acid. And really, it has to work harder or less effective in disinfecting the water. So it's a double-edged sword. What do? Right? You try to do the best you can, right? So for us here, we're about 7.7. It's enough of a pH rise that I'm protecting the pipes from any sort of leaching out. But on the flip side, it's not into the 8 pH range yet, which starts to cause issues with chlorine efficiency. So definitely something to really think about. And again, with algae too, right? Like an algae bloom, we talked a little bit about what happens at night in an algae bloom. It could make that water very, very acidy, pHs of the 5 or 5.5 and 6. Whereas during the day, it can make pHs higher. So yeah, it does change how water works. Algae is a nasty thing too. So for pH meter, again, really finicky things, and these are one of the most important meters, I think, in a laboratory, and it's the one that probably takes the most time or the most finicking around to make sure it's working. It's basically a measurement electrode, a reference electrode, and a meter with a digital and analog display, right, or some sort of display. They are calibrated always using buffers, right, calibrated buffers. And they should be calibrated all the time. pH meters tend to drift a fair bit, and it's always really important to make sure that you're keeping your pH meter calibrated. The 3 buffers that are used, and this could be a test question, are your typical 4, 7, and 10. And basically, they also vary with temperature. So always make sure in your pH meter that it has the words ATC, or automatic temperature compensation. If not, there's compensation tables that come with your pH meter, so that you take the pH and temperature, and then you have to do go to a chart and figure out what it really is. pH measurement at, say, 5 degrees is going to be different at 20 degrees. So you always have to make sure. A lot of the new units have this ATC already there. And so just please make sure when you have your pH meter that you know that it has that ATC. Typically, if you look at the probe of your pH meter, and if it has a nice silver cylinder or a little silver probe on the end of it, that's usually your temperature probe. And that means it usually does have an ATC, or automatic temperature control. So always make sure of that. That's something that's super important to make sure that you're checking at all times. Again, those 3 buffers are used to create that curve. And please calibrate these things all the time. I usually once a day, I will calibrate my pH meter. Okay, one of the more common tests that are done is chlorine, right? The chlorine residual. As an operator, this is probably the test that's done the most as an operation staff. So when chlorine's added to water, it reacts with the organics and pathogens or anything you're going to combine it with and cause reduction in the overall amount of chlorine in the water. If there's more organics, then more demand on your chlorine. That's pretty simple. That's your typical chlorine demand. The higher number of microorganisms, the greater demand for your chlorine or your disinfection. The total chlorine added at the treatment plant, less the chlorine that combines with the organics, is what's left over is the residual. That's what your operators will be testing for. And we'll look at a couple of different things here. There's a couple of different methods to test for chlorine. The 2 big ones are colorimetric or amphiometric. And but again, the most common one is a DPD. Now, back in day, and again, we'll go back to these color wheels, right? These color wheels are same thing. You can see here as I wish I had a light that I can show you, but you can see I have a color wheel here and I put my samples in here and try to figure out, can I see what's going on? And that is a very early chlorine tester. Again, very subjective, right? Because I have to hold it up to the light and I've got to figure out what's going on here. And it will tell you, well, that color is 0.8 or again, very subjective. It doesn't really spit out a number. Fast forward a few years, this is pretty typical, like the picture here. This is my old kit. Man, I've had this thing for like a million years. That's your typical DPD. And I mean, I still have this kit. It's been with me for a long time. I don't think that's used anymore. But basically, this is basically a light source with a filter. We're gonna fill our sample vial usually, right? You're gonna fill it and see that diamond on the front. It's really important to think about. As we talked about with the turbidity meter, right? Light's gonna shine right through here. And it's gonna shine through the sample and there'll be a detector at the head of these things. What's super important on your vial here is that my fingers don't touch this part. I don't want my fingers touching this part because that's when I put this into my machine, that light's got to shine through there. So if there's fingerprints or whatever, or if it's dirty or scratched, it's going to mess up your sample. Super important. Once you put the product in here and usually some water, fill it to the right line, right? There's usually some of these vials have a line on here and you fill it to the line, just like in the picture here. And then you're going to put in a powder pillow. Now, those are pretty typical powder pillows that we'll use. Make sure that two things on here that they're not expired. And this particular one expired in 2016. So this is not a real good one to use. That's why it's been in here. But make sure it's for what it's, this says chlorine-free DPD. So make sure it's the right one because these also come in total. You're going to put that in here. And the one big thing is that you want to make sure it's clean. These vials are really, I never want to see people do this and take paper towel and be really rough with it. These are really expensive glass vials. And they should have like special chem wipes and whatnot that's going to, you want to make sure that it's nice and clean and dry. And I always look for scratches and whatnot because a little scratch is going to really mess you up. The cleaner your vial, the better and more trusting your reading is going to be. Because when that goes in here and you shine that light source through there, you want to make sure that it's going through that vial, that the glass part isn't going to make your reading, that what's inside that unit is going to be compromised in any way, shape, or form. So you always have to make sure of that. Again, proper vial care, I don't care what unit you have. Again, I always hold it by the lid, and I'm very, very careful, or the very bottom. I try never, ever to touch that middle part, you know, and be very, very careful with it. Unfortunately, sometimes it's hard, right? Because we are out on the field with these units and, you know, it's raining or snowing in our case, it's cold, temperature, hot, but just make sure, you know, I can't stress enough on how important it is to keep your vials clean. Because if the vials aren't clean, it will cause you a whole lot of issues downstream. Talk a little bit about disinfection byproducts again. Again, it comes up a whole lot. Again, we had to balance the risks, right? We know that there's disinfection byproducts out there. And again, that's a big challenge for you guys as operators. You know, I'd rather have water with chlorine residual. I mean, the risks are there. I know that there's a potential to be sick with disinfection byproducts, but I can guarantee if I have water that's not disinfected, that I'm going to get sick. So I'd rather take the guarantee that, you know what, if I put chlorine in my water, I'm going to be safe. Then, you know, so you have to weigh those two things. By treating the water and knowing more about getting organics out of the water and protecting your watershed and getting the organics out through treatment processes before you put chlorine in the water is super important. And that's, I can't stress that enough. Again, it's only been in the last 30 years. There's a downside to water treatment. Disinfection byproducts, that happens. And we'll talk a little bit about a few other little things that are coming up. But again, these are unwanted compounds. And it gets worse when you add chlorine. You need to employ some other tactic to reduce disinfection byproduct formation. Again, I recommend that let's treat the water well. You know, get the more organics out of there. The more organics we can get out of this water, the better it's going to be. Less disinfection byproducts. So we try really hard to get rid of that. The two that are concerned, again, are going to be these two, trihalomethane and haloacetic acids. So THMs and HAAs. This keeps coming back, and I'm pretty sure you'll see this on my little 50-question test next week. So trihalomethanes are a big one. The one big thing about trihalomethanes is that, again, we know that chlorine is used, and it has to be used because most of our regulations need residual protection. And chlorine's the only thing that's going to give you a residual protection that we measure. Again, chloroform is one of the trihalomethanes. And when I look at my water quality tests, I'm going to look at, when it comes back, chloroform is usually always the highest. That's usually the biggest one that's formed, or the one that forms the easiest. It's usually called chloroform. Also, we see some bromo or bromide type concentrations. Also, I see a lot of those. Again, you have 100 micrograms per liter is a typical number that we try to aim for. And then this is a running average. So I'll take 4 samples over the year, and the average of those numbers have to be under 100 micrograms per liter. And where I'm going to test for trihalomethanes is usually at the extremity. And because that's got the most time for organics or contaminants to mix with the chlorine, and you're going to see these. So I always pick sites that are my extremities are the farthest ends of my system, because basically I've had enough time and chlorine contact to form trialhalomethanes if I do. For those of you who have rechlorination out there in your systems, that also can add to trihalomethane production, right? So you have maybe halfway through your system, you're reintroducing chlorine. That could also have a definite effect on trihalomethane production. So keep that in mind. Where I see it right now is, like I told you, I've got all winter flowing very low flows, and now my flows are starting to come up because people are turning on their irrigation, and that causes right away a lot of organic material to get moving in the mains out there, and that combining that with the chlorine, that we get into some troubles here. Before we move on to the next topic, one other thing that's coming up, and I hear about it more and more and more, and I don't have a slide on it, but we'll talk about it quickly, is that other concerns in water are going to be stuff like birth control and pharmaceuticals that are in the water. And again, current treatment processes on the wastewater side don't have a way to remove that. So with all the pharmaceuticals that are taken by us individuals and end up back in our waterways, right, through the wastewater treatment system. So, that could be for antidepressants and any sort of medication for, whatever, even birth control and all that ends up back in our water cycle. And these, because they are not easily removed in a wastewater treatment process. And so now these are starting to come into our treatment plants. And again, because they're dissolved and they're not easily removed, there's no mechanism. And then also too, think about, we add chlorine to these things. So we chlorinate different things. What are we creating in compounds? So as we're moving forward as water treatment professionals, always keep that in mind, that there's always things that are going to come up here. And I think the next big one of concern that we need to be all aware of is that there's going to be these pharmaceuticals and whatnot that are in that aren't removed in the wastewater process, get back into the system. And now potentially when we add chlorine to it, it could cause us some issues. The other big one too that's coming about too is stuff called microplastics, right? And we're seeing some of these now starting to surface in our, and they're so minuscule that they're getting through our processes. Again, they're not causing us grief from a treatment process, but again, these microplastics or these little things are in our water systems. We're starting to see them more and more. So keep in mind, as water quality changes, you guys, and water quality treatment changes, these are some of the more emerging things that are out there, and we have to be always aware that things change very, very quickly. So what do we sample, right? We want to basically make sure that drinking water is safe to drink. That's our number one job as operators, right? We also want to meet the requirements of our regulatory body. For you guys as operators too, you want to make sure that the quality of your source water or quality of the water leaving is consistent and hasn't changed. And so that you guys can make any sort of operational changes, whether that's to chlorine dose, coagulant dose, whatever you need to do to keep our water good. You also good to document the water quality. You want to know if there's going to be changes. Respond to customer complaints. I have a team of operators here, and if we get a complaint, I'm going to send them out and investigate what's going on. A little bit harder with the COVID right now to actually deal with customers, because I won't let them go to people's houses. And even for our sampling, we have to really make sure. It's hard for us to sample locations because it's so cold. things freeze. So we always go into we had buildings that we would go into, schools and stuff like that. But because of the COVID, we've not gone into those buildings. And so we're very careful about how we do our sampling, being very safe for us. So responding to customer complaints. It just changes things a little bit. Where to take samples. And again, follow your guideline and regulations. I would say, let's get something representative of, an extremity is a good site, but in the start of your treatment plan, it's a good site. Those are your start and end points. But you also want to go in between in a number of key locations. You're not going to choose all dead end sites because that's not representative of what 80% of your customer base is going to be drinking. So find spots in your distribution system that's going to be representative of the entire whole of your system. You're going to also look at making sure you're taking samples of your raw water. For us here, because I have a lake and a creek, I'm going to be taking samples of those. I'm going to take samples of the water leaving this plant here, and I'm going to take samples, and I got two major extremities that I'm going to look at. So I'll make sure that I take samples from there, but also in between to make sure that I'm getting representative samples. Read your guidelines too. Depending on what you're sampling, you'll have to take different types of samples. The objective of sampling is to take a portion of material small enough in volume that you can do your test and it's transported, but again, it's enough that you can get all your testing done. So if you need 100 liters for this, 200 liters for this, so make sure you get enough product in that bottle so you can bring it back to your lab and get it done. All right, so this is, before we go to microbiological samples, I'm going to show you a couple of things here in regards to sampling. So this is a collared system, as you can see in the picture here, and it has a sealed bottle. This is a way to do an in-house sample of water. It is a collared process. I mean, that's an older one that I have here. That's a newer one here, collared. So basically, really, really important, wash your hands first, right? Keep your hands washed. And so what you're going to end up doing is you come to your sample, you want to turn on your sample port. And I recommend like a 1/4 inch copper or something that's going to give you nice. I don't want the water spitting all over the place. It should look like a pencil, width of your pencil coming out of the tap. It should be nice and uniform, and they call that a laminar flow. It shouldn't be all like fizzy. And first of all, though, if it has an aerator on there, take that aerator off and make sure that you're able to, because I've seen a lot of aerators. If you ever take an aerator off and look inside it, it could be pretty nasty on the inside of that, right? And you want a more representative sample. So then you got your tap running. It's going to be cold. Remember that, it has to be cold. Don't use hot water. And you have a little bit of, you got this nice stream out there. I'm going to show you two different styles of microbiological bottle. You can see this one here, it's sealed. It's got a ring around it. At no time, though, do you want to put your fingers in this area here. I always keep it down low, and I'm going to take one hand and I take the seal off of it. So I'm ready to go. I'm being very careful because as I'm doing this, two things here. I never, ever will touch the threads in here. And if you touch any of this like I'm doing right here, the sample's no good. You got to throw it away. Don't touch it. The other thing I'm doing too is keeping the lid down. If I do this and do the lid like that, airborne bacteria can get in here. So I'm very careful. I keep the lid down here just like that. I'm going to fill this to the 100 ml mark, and there is a 100 ml mark there. And then once it's full, I actually just set the cap back on there. if I'm doing an in-house sample, I'm going to put my own bug food. Remember those trays, those pink trays of bacteriological? We're going to see them again coming up here. Now I take this and I'm going to, inside here, there's some bug food. And it does the same thing as that pink agar solution that we saw earlier. And we put this into the bottle. And again, keeping your fingers off the critical areas. You give it a, you can give it a kind of a, and you can actually put this whole bottle into an incubator. You can see the incubator in the picture there. Now, and that will just tell if this turns yellow, then it's a positive. And if it stays clear, it's a negative. It doesn't give me any numbers. It just tells me, is it there or is it isn't? Now, the other option to do is actually I pour the contents of this into a tray. And you can see these trays here. Each tray, there's a bunch of squares on this tray. And what happens is that the squares will light up yellow if there's any sort of coliform bacteria. If there's E. coli, I can put a black light across it and it will glow. And this is all done in-house. My guys are getting ready to sample today, and this is a bacteriological bottle that I'm going to send to an accredited lab. It's going to be handled in the exact same way. The lid is nice and sealed. Basically, always wash your hands. You got your sample tap running. You're going to take the lid off, being very careful never to put your fingers on the threads or anywhere where the water would touch, else you could get a positive sample. You take the lid off, you fill the sample to the line. You can see it's really important. There's your line right there. And then keeping that lid down, just like what we did before, and then put the lid on here, and then it's nice and sealed and you're ready to go. Now, these bottles here, don't leave them on the dash. Don't put them in a cooler. Try to keep the temperature at about 4 degrees, like a fridge temperature, right? Don't freeze them. And that's one big problem for us. We actually almost have to keep them heated in a car so that they don't freeze. And then also be very careful with shipping. Again, bacteriological samples are collected in bottles that have been sealed and sterilized, and they got a chlorine deactivator. So if you can see here, I don't know, you can see the kind of the powder that's at the bottom of this particular bottle. This is sodium thiosulfate. You also see it in the IDEX bottles here. You can see that inside there, those little crystals. Don't wash those out. Never ever rinse a bacteriological bottle. It's made to open, put the sample in and turn it. Don't rinse the bottle ever. Don't rinse it. Don't put your fingers onto the threads of that bottle. Again, these bottles can be obtained by a certified lab. The IDEX I have to order, but the ones that are going to be to an accredited lab are owned by the accredited lab. They usually have all the proper information about the lab on the bottle and stuff. And again, like I said, in-house microbiological sampling could be performed with a presence-absence call alert, and that's that one I showed you a little earlier. There's different types of samples out there, and this shows up in the test a lot, is a grab sample. And a grab sample is collected at a certain time and place. It's a one-time sample. Composite is that it's a series of grab samples. So I will take one at 2 o'clock, 4 o'clock, 6 o'clock, and I'll mix them all together as a composite. And the last type is called an online or continuous one, that it's always automatically measuring, right? And that's what we see a lot with turbidity and chlorine now with these new analyzers that are at your plant. They're always measuring the component. Again, online's a big one, right? That's automatic measurements. That's been fantastic for us as an operator to always be seeing what can be done there. Again, always make sure that you're testing for chlorine turbidity. That's your big ones. That's going to tell you what's going on out there. Again, two things to note here. Accuracy of the analytical result is only as good as the care that was taken in collecting the sample. No sense reporting something that, you know what, there was really, they didn't take a lot of time and actually making sure that the sample was proper or representative. And I agree with this statement. The collection of a bad sample or a bad laboratory result is worse than no result at all, because you have to deal with it. This is a result that you got. And so it takes a lot of work to make sure that your water is going to be safe. So some handling rules in general, right? And again, you're required to ensure samples are collected properly and that yourself and your staff are trained to collection procedures, making sure you've got the right containers, they're labeled correctly, all the proper chain of custody forms are done, that they're transported properly in a proper container, right? And that they're not allowed to get hot or they're not allowed to freeze in our case here. If you don't follow these, you know, big one here too is time period for delivery. We have 30 hours. Right, that sample has to be processed within 30 hours. So our samples here, we take samples, so it takes all day to do the samples. Then we have to send them via a courier to another town. That another town, they get them delivered, I hope, and then they have to process those all within 30 hours. Have we failed that? You bet. You know, on a snowstorm or something happens and the samples don't get to the location it needs to get to in the right time, then we have to sample all over again. And that's a lot of time and money every time that happens. For chlorine residual testing, right? Again, follow the guidelines, right? Again, you want to make sure that it's representative, that you're, you know, you need to be also testing dead ends and making sure there's chlorine residual everywhere. You've got to record date and time, location, sampler, right? Maybe there's a weather condition or something, but always make sure that you're following all that. I always, it says here, do residual testing with microbiological. I always do that because if I have a good chlorine residual and I get a total coliform, that tells me maybe my sampling isn't right. Okay, so always make sure. And I always like to make sure that I'm testing total chlorine and free chlorine, and it allows me to see what's going on there too with combines. Okay, some more general sampling guidance, and especially when it comes to the microbiological stuff, right? E. coli and total coliforms. So making sure that we're making sure that they are, you know, for you guys as a sampler, we're not touching those threads, you know, we're not putting our fingers on this part here or in here, never ever. That sample's no good, it'd be thrown away. Making sure that if there's any sort of special preservatives that have to be put in, that you're following the directions that the lab gives you, so that you're making sure that these samples are going to be the best samples that you could possibly get. Handling and storage, you know, it's super, super important. Again, there's different stuff that can be done in labs and stuff that could be done in an accredited lab. Like for us, we can do almost everything here except for the major metals and that stuff that's done every few, you know, every probably 3 months we send out stuff to accredited lab. We also don't do the bacteriological stuff. We do some of the in-house stuff, but this always, we do 6 samples go to an accredited lab every week. When it comes to coliform testing, there's a couple that are you know, the most ones that are used are the MF method, and that's used a fair bit. That's that one that you saw earlier with the agar plate, just like that, right? You put the sample in here, there's a media in there, and it grows those little bubbles, and then we count out the bubbles. Most probable number, again, that is the ones that we saw earlier here, right, where we count up the squares that are glowing, and that is the most probable number. A presence absence would be a good example of, is it there or is it not? And I mean, we saw that if I just use my, that's a P&A. If I just put the bug food in and put this thing in the incubator and it comes out and it's clear, we're good. If it's yellow, we're bad. We also talked about the HPC, right? The HPC was those other dots, where the coliforms were those nice big round pink looking dots, where the heterotrophic, you can see the one on the right here, it has darker circles and darker spots, and those are going to be for HPC, and that is a heterotrophic plate count. These are not coliform bacteria and not bacteria that are going to make you sick, but they're definitely indicators that there's bacteria in your system and that you should really start to think about flushing that system a bit. Depending on what you're looking for, like I said, typical for you guys in your line of work, and when we're doing coliform testing, we're going to be using that pink broth on the left here. And that, and then here you can see, even if you look, you can see different colors, and different bacteria will fluoresce different colors. And that's what you're kind of looking for. The one on the right, different type of media that's in it, but the same thing, it's going to grow little dots. Each color of dot represents a different type of bacteria. And I hope that there's going to be nothing, but sometimes that happens. All right. Unfortunately, things happen, right? Sometimes you get results back that's going to be not what you really want. Make sure you guys have a protocol to do. If you have a bad chlorine residual, what are you going to do? I always like retesting first. That's always going to be your first thing. And even with the bacteriological, right? If I get something bad that comes back, the first always thing I'm going to look at is, okay, was there a chlorine residual? If there was, maybe there's an issue here. I will always go and resample. I let my health authority know, but then I go back and resample, and I sample that up. And if it's good, we're good. If it's bad again, then I would do action, whether I flush that reservoir or redo a number of things, but I make sure that things are going to be clean, and then I resample again until such point where I'm happy that the water is going to be super clean. If you do get an adverse water quality event, know what you're going to do. Know who you're going to call. Have an emergency response plan. Like, I can't stress enough to have emergency response plan. And, so that and when this happens, and that your operators are trained, this happens, who do I notify? Who do I talk to? What am I going to do? Right? Also important to know your system. If there's going to be issues with your system, knowing that I can shut this reservoir down, I can clean it and get it back online, or disinfect, or, does this affect my whole distribution system, or does it affect just a small portion of my system? So always make sure that you understand, how your system operates and where the sample came from. Always look at the science, because I can't stress that enough. Okay. And again, algae, right? Again, I always like to throw that in here because algae becomes a real mess for us. So if you see some really weird wonky numbers, especially when it comes to pH in your water and you're getting some taste, always look at your source water for algae. Algae makes a huge mess of things. So always make sure of that. One thing we didn't talk a little bit about is the oxygen demand, right? And some plants will actually measure with a DO meter the oxygen demand of your water. And if that's starting to change, that can tell you that potentially not just algae, but plant life or something's in there that's causing the pH to fluctuate, and that it's eating up the oxygen component of it. So always be aware of that. Algae is a really nasty thing. All right, everybody, that is my last slide for today. And again, you've now received 11 weeks of lectures with all the information you're going to need to really be successful at your ABC exam. And so my big thing now is going to work I got 50 good questions for you guys for next week. I really want you guys to come prepared next week. It's gonna be very interactive, so be very ready for that. I'm gonna throw questions out there and you guys are gonna answer them. And if there's an issue with one of those questions, we will have a discussion at that point. But I expect you guys to review your material and come prepared, and we'll get you ready to be very successful in your exam. Ignatius, when's the exam date for these folk?
We were programming for, I think it's the 16th to between the 16th and the 19th. So what I will arrange for Suzanne perhaps to will send off an email to those who are doing water treatment to confirm all of those dates. And we should do that by tomorrow or so. Okay. The other thing is, I just wanted to, so you're saying next week we're going to meet with you and you're going to issue the exam.
Yeah, I got an exam. So basically it'll be a slide exam. A question will come up as a slide. Okay. And I'm going to have you guys out there, you're going to answer via the chat, and it'll be A, B, C, or D. So when we do it, we'll do it through the direct message, so not everybody can see, and only I can see the answers. And then we will have that discussion at that point. Okay. All right. I'm just trying to, because Mike Epen sent me his questions and I was trying to figure a way to get them to do it. This is the easiest way, like for me, because I can throw it on the slide, everybody sees it. And then I use the direct method, so not everybody sees it, but I'm the only one that will see the answers coming back. So then I can do it that way. It's an easy way to do it, and I think it'd be really anything that I can see. So say if I see half the class or more getting the answer wrong, then it tells me that I need to explain that a little bit better. So I've picked really key questions to help generate some discussion. And that's kind of the goal of it. I think, with the material that's been put forward, there's some good material there. So if you guys, go through the lectures again, I think you're going to be really successful. Okay. Yeah. All right. Well, thank you so much, Mike. I hope your coffee is working for you. It's starting to kick in now. We're good. Okay. So see everyone next week and get ready. I hope you're doing the revisions. You know that we have all the tutorials are uploaded in YouTube, so you can go to the platform CAWASA tutorials at YouTube, and you're going to find all of them, and you could do your revisions from that if you don't remember. And you need to also do a lot of reading, so please do that, and see you next week. And thank you very much, Mike. Yeah, have a good day, everybody. Have a wonderful day. Bye-bye.